So today we're talking about bonding between atoms. A little bit of review here. How many valence electrons in an alkali metal? What are you probably going to need every time you learn anything in this class for the whole rest of the year? Look at the motion in the classroom. Yes, she's just held up a periodic table and she's proud of herself. That's good. Yeah, periodic tables, just an essential piece of equipment anytime you're taking the class called chemistry. If you need to borrow one of the laminated ones, they're rented out for $15 a minute. So you find the alkali metals on ye old periodic table. Which column are they in? 1. Which coincidentally is the number of valence electrons they have? Did you know that? And then group 2 has 2. In fact, it's so easy. I'm going to insert a little page and draw the world's most haphazard periodic table. It goes 1 valence electron, 2 valence electrons all the way across that gap, and then 3, 4, 5, 6, 7, and the noble gases have 8 every frickin' time. Why is that? Well, this random element here would be S2P3. What is 2 plus 3? 5, and it's in that column. So if you need another number of valence electrons, you just kind of count across in slow motion. 1, 2, 3, 4, 5, 6, 7, 8. That works for every element except for helium. Not helium, but helium. Helium just has 2, because really it should be right there. It's a 1s2. Hey, Mr. Murphy. Yes, guy with the curly hair. What if I was this element here? 1, 2. It's a 2. All right? Because this element here might be 5s2, 4d6. Let's just pretend. 5s is the outside. Valence electrons are only the outside. So the 4d is lesser and doesn't get counted towards the valence. Cool? So it's a lot easier than actually having to work out the whole electron configuration, isn't it? Most elements want to be like noble gases. Noble gases have 8. More on that in a little bit. I hate when people say more on that because it sounds like they're saying moron, but they're not trying to. How many valence electrons does hydrogen have? Let's go, you with the red sleeves on your shoulders. 1. True. How many valence electrons do the halogens have? Guy with green folder back there. Halogens. 7 it is. The halogens have like fluorine and chlorine in them. Ooh, draw the electron configuration. Draw the electron configuration for sodium plus 1. Sodium's 1s2, 2s2, 2p6, 3s1. Is that it? 11 electrons? Ah, but it's a plus 1, he says. So I should do what? I'm going to take the last one away. Because if you were taking something away and they're in layers, let's say that you have a stack of bricks in your backyard for some reason, which brick are you going to take first? The one on the very bottom? You can't get to it. It's underneath all of the others, right? You have to take from the outside in unless you're a magician. And are you a magician? No? Okay. So, you have to take from the outside, so I took the 3s1 off. That's the configuration of sodium plus 1. Chlorine, minus 1. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Except it's a minus 1. Where do you think that extra electron is going to go? 3p6. 3p6. Take a look at this thing. This has how many electrons on the outside now? 8. This has how many electrons on the outside now? Magic number 8 appears again. It's like a crazy 8. Things want to become 8. A lot of times the elements on this side will lose their 1 or 2 valence electrons and drop backward into 8. On the other side, these elements here will gain like 2, or they'll gain 3, or gain 1 to get to 8. Metal or non-metal? That's an essential question you need to be able to answer. Find on your periodic table a little stair step that separates the metals from the non-metals. On your periodic table, about here, it goes troop, troop, and then this direction it says metal, and that direction it says non-metal. True? There he is. We missed you. It's good. Thank you for coming. I just recorded that interaction. And I'm still recording. Okay, stop. And so this does something like that, right? In my haphazardly drawn periodic table. So let's pick an element. Iron, metal or non-metal? If you had to look, that's not good. Iron, definitely a metal, right? Oxygen. So if you ever get lost, those are two simple ones. Like if you can't find this on your periodic table, go, oxygen's not a metal. Iron is. And then where people get confused is they say calcium. And they're like, calcium, I drink that. It's probably a non-metal. No, it's a metal. Your bones have metal in them. It makes them stronger, right? If they were made of non-metals, they'd be rather brittle. That earned a smiley face. All right, let's go back. Last question. So we could just basically pick the replacement out. So let's just holler these out. Sodium, metal or non-metal? Bromine, metal or non-metal? Non-metal. Titanium. Nitrogen. Oxygen. Calcium. Metal. Zinc. Phosphorus. Fluorine. Barium. Metal on the far left underneath like magnesium and calcium. Cesium or caesium. I can't say it the other way. Cesium. Yeah, super reactive metal like used in explosives because it's so reactive to water. You could just pack cesium into a hole and then pour water on it and it explodes. Of course, it's really expensive. Just use dynamite. Aluminum. Just barely a metal. It's right on the line, isn't it? Huh. Sulfur's a non-metal. That line, when it rides the line, they're typically called semi-metals or metalloids if they're on the line because they're a little bit of both. Metals are typically hard. Non-metals are typically brittle and fall apart. Metals typically conduct electricity and heat. Non-metals don't. And they don't do it well. Not to say they don't, but just don't do it well. Aluminum conducts heat really well, not so much with electricity. All right. So, we're talking about bonding here in this chapter. And bonding is what holds us together. Excuse me, I'll wipe my hand off here. Bonding is when two elements come together and they hold on to each other. What would cause the two elements to hold on to each other? What in one element is attracted to what in the other element? It's all electrons and protons. My electrons are attracted to your protons are attracted to my electrons, and when they come up to each other, they grab onto each other and they start to yank on each other as hard as possible. That hold, that pull, the force is called a bond. All right? The force that holds them together is called a bond. There are different types of bonds. There is a bond where two people come up and they're like, "Hey, how you doing? It's good to see you again." And they're really like holding on and they're sharing and it's equal. I can't rip her arm off. I'm trying to rip her arm off, but it seems to be attached. Right? So do I own this hand? No, we're currently sharing possession of these hands. Now, if I was to grab on and go rip and just walk away with this arm and I possess it as mine, I use it as a club or something, that does kind of chemically exist. There are different types of bonds. It's a stupid example of covalent versus ionic, and we're going to hit that again. The key, though, is really in their valence electrons. The closer an element is to getting to 8, the stronger it is. The farther away from being at 8, the weaker it is. Here we have a bunch of different bond strengths. These are just between two elements. And then how much energy you had to put in to break these bonds apart. Can you find the element or the combination that has the highest value? Which ones have the highest value out there? Say again? Hydrogen and fluorine. Where's that? Right there? That's pretty high. All right, yep. Oh, you can count that. Oh, look at that one. That one's pretty high, isn't it? Have you ever seen nitrogen bonded to nitrogen? Carbon and oxide, it's carbon monoxide. Have you ever seen nitrogen bonded to nitrogen? That's what's in the air right now. 70% of what you're looking through is nitrogen bonded to nitrogen. What's it look like? Like this? Like that right there? I'm pointing at nothing, right? Because in air, these nitrogen particles are so far apart, the light gets right through without us even really noticing it. You've breathed this molecule, nitrogen to nitrogen, in 1 million times in your life, and you're probably going to breathe it in 1 million more, 1 billion more. You've never broken it apart. That bond is too strong. It's too difficult to break. A lot of the other bonds are weaker. You can break them apart. Where's oxygen to oxygen? Right there. You breathe in O2. Do you use O2? Does your body break it apart? Yeah. Your body combusts things with oxygen. It moves the oxygen into the cells and burns the food you eat. Alrighty. So let's first talk about ionic bonding. Ionic bonding is really more about theft. Two atoms come up to each other, and the atom that's stronger just takes the electron and walks away. And now that electron, you just got a tweet or something. And now the electron belongs to that atom and not to the other atom. After this electron's been shifted from one to the other, both atoms have a charge. What charge do I have possessing the electron? Negative. And what charge does she have? Positive. I'm also positive she's angry because I took her phone. Here you go. You can have that back. Thanks for the prop. Electrons get transferred between metals and nonmetals. Nonmetals are stronger and smaller. I don't know if you remember the trend when we did the periodic table trends. Let's just insert page here again. Which element was the strongest and smallest on the periodic table? Helium. He is small and strong. And which element was the weakest and largest? Francium is big and weak. So what's this mean? If you have an element from this side of the periodic table bond with an element from this side of the periodic table, the difference is so extreme. These are so much stronger than they are that electrons get ripped off of one element and shifted to the other. We call that an ionic bond. That's the wrong direction. We call that an ionic bond, where the metal loses electrons to the non-metal. You could look at this the exact opposite, though. Couldn't it possibly be that the metal comes up and goes, hey, you're going to take my electrons and you're going to like them? That's also kind of possible. Francium is kind of so weak it just gives them away. Francium actually doesn't exist on the planet except in like 1 or 2 grams because it's so radioactive. So maybe cesium. Cesium is so reactive it gives its electrons away to water, breaks the water molecules apart, frees all the hydrogen, but then it gives off so much energy that the hydrogen spontaneously combusts and causes an explosion. So the cesium is so weak and it gives off its electrons, it forces the others to break. Ionic bonding. The key is this. Circle metal, circle non-metal, arrow, arrow, emphasis, emphasis on the important thing. Transfer electrons. We have charges afterwards. Hey, Mr. Murphy. Yes, new girl. What if it was two nonmetals? If it was two nonmetals, who's stronger? The strong or the strong? Really? All right. That's not ionic bonding. That's a different category. There's going to be different categories of bonding. There are about 17 different categories. How about we just learn 2? We'll cheat and talk about a third one for a second or two here. But really, we're going to learn 2. The strong versus the weak, ionic bonding, and the strong versus the strong. If 2 super strong people come up to the same sandwich, who gets it? He said, me. Pointed at himself. He needs to... did you say guess? He said yes. They end up sharing. It's not sharing because they like each other. It's sharing because they can't steal from each other. It's the exact opposite of the kindergarten version of sharing. Right? Kindergarten version of sharing, like, you know what? You should also be allowed to play with the Play-Doh. Here, though, it's like, I can't beat you up and you can't beat me up. Let's share. Yeah, that's nature. That's not classroom. When we do these reactions, though, with ionic bonds, I want to make it clear it is never one atom and one atom. It is actually hundreds and hundreds of atoms. Salt or sodium chloride is never 1 and 1. That's the ratio of sodium to chlorine. For every sodium ion, there is a chlorine ion. It is a 1-to-1 ratio. But it might be sodium 100, chlorine 100. When you have salt cubes, it just depends on how big the salt cube is as to the number of sodiums and chlorines. It's very different from molecules. Ionic compounds, we're just looking at the basic ratio of elements. It looks pretty cool. I like that. Covalent bonding is between nonmetals. Let's break the name apart. What is valence referencing in the valent? Which type of electrons? Say again? The valence electrons, the one on the outside. What does the prefix co mean? Say again? Share or work together. So they're sharing or working together. They're valence electrons. What about the inside electrons? Don't care about them. You can't get to the middle without going through the outside. It's just the outside that we care about. So it's the outside electrons that are being shared. So here's a drawing. It's called a Lewis drawing, or Lewis dot diagram, where we've taken nitrogen. Nitrogen on the periodic table is 1, 2, 3, 4, 5. Is that true? Is it about 5 over? And I'm going to just throw the 6, 7, 8 up there also. So I put 5 electrons around nitrogen. What did I use to represent the 5 electrons? This magical thing called dots, right? Made 5 dots to represent the electrons. How many more does nitrogen need to get to 8? I'm being shown 3 fingers. Yeah, 3. It needs 3 more electrons to fill up the remaining space. These hydrogens each have 1. So if the nitrogen shares, and shares, would the nitrogen appear to have 8 through sharing? Yeah, that's a very different scenario than the other one. Instead of theft and possession, it's sharing and possession. So covalent bonding does something differently. They share electrons, and now we have 1, 2, 3, 4, 5, 6, 7, 8 after the sharing has commenced. What about the hydrogen? Hydrogen had 1. Now it's sharing. How many does the hydrogen have? 2. What element has 2 valence electrons? Helium. Is that a noble gas? So hydrogen wants to look like helium, also a noble gas. Here we have fluorine with 7. It's bonded. Fluorine with 7. It's bonded. Now they both have. See, I can't hear you. It went from 1, 2, 3, 4, 5, 6, 7, and now it's sharing, so it also gets to count this one. These get counted on both sides. So they both have gotten to 8 via sharing. That's going to be our goal. Our goal is going to be to connect elements together to try to get them to 8. One thing we need to think about is how strong the elements are. The one trend we're talking about this unit is electronegativity. Electronegativity is the strength factor. Need to leave? Good luck. So imagine for a second we stopped class and we just had a tug of war. All right? So I take you, sir, and I put you against her. All right? Ready? Tug of war, commence. Up. He won. Sorry. All right? Then you against her. Oh, you won. And then you against her. You both fight for 20 minutes and no one wins. Oh my gosh. It's the longest tug of war ever. Could we do this and have like a class ranking of tug of war? We could even throw New Girl in there, right? We could have a class ranking and find, hey, look, you're just as strong as her. Must be the power of curly hair. I don't know. Would there be a couple of ties? There would. But we could have a class ranking. And then eventually we would know if we put you against him over there in the corner, you're exact opposites in the classroom. You're on the weak side. He's on the strong side. Small and strong, big and weak, just like the elements. And so in that tug of war, you destroy him. You're just like, boom, rip the rope right out of his hand. And he's like, oh, my hands. The periodic table, someone has done this, and they've ranked them on, of course, a 0 to 4 scale, because 4, that makes sense, right? The ranking is called electronegativity. It's the relative ability of an atom to pull shared electrons to itself. So if they try to form covalent bonds, how are they going to share them? There is something weird about this periodic table. Can you figure out what's weird? Yes. Okay. They did expand this zone out. They expanded that out because these elements at the bottom kind of fit into there. It's missing helium. And the rest of the noble gases, isn't it? Why is it missing them? Because here's how they interact. Okay, so I come up to you, I'm like, okay, we're going to make a covalent bond. Ready? No, we're not, because she doesn't want to hold my hand. She refuses. She's a noble gas. No bonding occurring. That's what they do. You stick your hand out there and they go, I don't want your hand. I won't bond with you. I totally get that. I don't want to hold my hand either. But they're attached to me, so I'm stuck. These elements don't bond. So their value is a 0. At the same time that it's a 0, you could also look at it as like infinity, because they're so much stronger than all of the others. Welcome back. You don't have to have these memorized by any means. Usually all we do is say things like, as we get closer to this side, they get stronger and stronger, and fluorine is by far the strongest. Fluorine is so strong, it's almost impossible to contain. Have we ever talked about how you contain fluorine? No? Correct. Yeah. You fill the container with fluorine, it burns the inside of the container, and then you can then fill it with fluorine and it'll store it, because the inside of the container is already burned. It's like coating the inside of a house with ashes so that you can't burn the walls because what's exposed has already been burned. It's kind of weird. That substance that they coat the inside of the bottle with is called Teflon. Teflon is used on pots and pans, right, to make them non-stick. So they coat the inside of the can with graphite. They then inject fluorine gas into there, but they can't store the fluorine. They have to make it and then jet the gas they're making into there. and it burns the inside in one of the most wicked fires ever. And then the graphite is converted into Teflon. Teflon is carbon coated in fluorine. So then the inside has carbon coated in fluorine until it can't react anymore. Then you can fill the container with more fluorine. And you have a portable fluorine container for fires at whim. It's more reactive than oxygen. That's a 4 versus a 3.5. If you got exposed to pure fluorine gas, you would immediately get burned. Well, actually, if you get exposed to pure oxygen, you're also going to get burned. You can't breathe in pure oxygen. Your lungs will burn. This is just like electronegativity. The closer you get to francium, the weaker it is. The closer you get to helium, the stronger it is. Just 1 second. Okay, no. Polar bonding. So, Samantha and I hold hands. I am far stronger. That's not going to work. Never mind. All right. Yeah, that's right. She pulls back. So we have a tug of war. Who's stronger, though? Me. But she's pretty strong. She's way stronger than Samantha. Samantha was like, please hold my hand. So when she and I bonded, I was like pulling and there was no resistance. That would be ionic. If there's no resistance, the electron gets transferred. If there's resistance, then it might be equal or it might be unequal. If it's sharing, but it's unequal sharing, then we call it polar bonding. Are these two elements the same strength? Well, let's go back. Fluorine is a 4. Hydrogen's a 2.1. Are they the same strength? They're not. Now, that whole trend thing we just did has one weird element. We're going to use hydrogen a lot, do you think? Yeah. And it doesn't follow the trend. What element is hydrogen just as strong as over there? Look at that list. It's almost as strong as boron. It's a little stronger than boron. It's 2.1. Phosphorus. Yep. So I'm going to write the H right there beside the P. Can you remember that P and H are the same strength? So if you compare fluorine to hydrogen, fluorine's is stronger than hydrogen. So the bond between them isn't going to be even. It's going to be shifted towards the fluorine. That's called a polar bond. It's an unequal sharing. They're still sharing because they're both pretty strong. You don't have to have these values memorized, but what we do is we compare the two strengths. So did I actually give you this periodic table in your notebook? Okay, great. So we just said hydrogen was 2.1. Which is stronger, hydrogen or hydrogen? They're equal. So is that going to be covalent, polar, or ionic? The difference between 2.1 and 2.1 is nothing. So that would be covalent. Keep going here. What's oxygen's value? I don't know oxygen. Yep. And hydrogen's 2.1. What's the difference between 3.5 and 2.1? Is that 1.4? Is that what you said? So, that would be considered polar covalent, wouldn't it? Because when they're sharing, it's not exactly equal. I get the hiccups. New girl. All right. We could do this with each one. We could compare the values and figure out which one's the most polar or least polar. Let's keep going here. I think chlorine is 3.0. I don't know sulfur. What's sulfur? And what's fluorine? Oh, no, fluorine's 4. Again? So I'm just doing subtraction here. 3.0 and 2.1 is 0.9. 2.5 and 2.1 is 0.4. And, ooh, that's a 1.9. Dang, that thing's so different. It's practically ionic, isn't it? Yeah. The difference between fluorine and hydrogen almost makes it look like it's going to be ionic. And it is somewhat ionic. So we could just subtract the two, and then they're given these kind of random arbitrary barriers that we describe the bonds different ways. Right. The other thing with polar molecules is it is rarely... Can I hold your hand, Patrick? Kirsten, can you hold his other hand? Turn slightly, like turn your body. Kirsten, pull as hard as you can. It is rarely just one atom pulling on one atom. Wait, keep pulling. Could be at different angles, couldn't it? No, I'm not going that way. It could be at different angles, and depending on the angles and depending on the atoms, I would guess that Kirsten and I are not quite the same strength. I probably have twice the mass she does. It's all the iron I eat. And therefore, I could probably pull with greater force on the central atom, called Patrick, than she could. But we're going to look at these. There's a trash can right there. We're going to think about these and how they're built and whether or not they are built and balanced properly. Both of the drawings on the board have a central atom with exterior atoms, a central atom with exterior atoms. Which one, though, looks like it's balanced and that the central atom isn't going to be going in any particular direction because it's being pulled opposites perfectly? Which one looks like it's being pulled in opposite directions perfectly? The CO2. The CO2 is nonpolar because the oxygens would be pulling each other and balancing each other out. It's oxygen pulling on carbon, and they're perfectly opposite of each other. However, and I'm building a model kit that you at home can't see. Here, sound effects. There, that sounded right, didn't it? Here. There, that's a good sound effect. When we build the water molecules, the hydrogens are not actually opposites of each other because there's also electrons in there. There's electrons on this side and on this side of the oxygen that push the bond around. So when they pull on it, they are not pulling opposites of each other, so they can't cancel each other out. This molecule would be polar, and that creates some really unique issues within water. Because it's polar, it has a negative side and a positive side. A negative pole and a positive pole. That's literally what the term polar means. Positive poles and negative poles. Another term that's often used right at the same time is dipole. That doesn't mean you're like trying to kill someone. Dipole in this case means two. Pole means positive, negative. There's a positive pole and a negative pole. What is this blue thing going down to? So that's what I was kind of talking about. We're looking at whether or not the atoms are evenly distributed, opposite sides, or are they not evenly distributed, kind of like I've got here. I typically think about symmetry, about the molecule symmetry. So here's one I'm holding in my hands. Does that one have symmetry? Would the white atoms be pulling on the purple atom equally? Yeah, they'd be balancing each other out. Whereas here, the green atom is not being pulled by the white ones evenly because they're both going up. They're not actually opposites of each other. And that's because these extra electrons on it. So symmetry is a good way of deciding whether or not something's polar or not. If something is off balance or asymmetrical or uneven, it's then going to be polar. We already hit on counting across the periodic table. 1, 2, 3, 4, 5, 6, 7, 8. Lewis structures. Lewis structures are just the act of representing the valence electrons as dots. How many valence electrons would calcium have? Find calcium. Being shown a certain number of fingers by one person. Find a couple other people looking for calcium. I got a 2 from her. 2 on his forehead. 2, 2. Yeah, 2. How many would bromine have? See you. You do it in Roman. Here you go. Roman numeral 7. Right? No? I mean, pause. And that's one of the most important things you'll ever know in life. So, we had bromine has 7 here. There we go. So I put 7 haphazard dots. When we're making dots, let's be careful. Let's not kind of go, like fluorine has 1, 2, 3, 4, 5, 6, 7. Fluorine has 7. See, I put 7 dots. Where the heck are the 7 dots? Are you counting this one? Is that it? What is that? Come on. One of my primary jobs in this chapter is going to be counting the number of dots you made. So make the dots carefully and with extreme prejudice. Feel free to make the dots like 1, 2, 3, 4, 5, 6, 7. Make them pretty clear when you're doing it. When we are bonding, there's a couple of rules we're going to try to follow. We're going to try to figure out how many electrons an element has and how many more it needs. We're usually trying to satisfy one of 2 rules for the needs. It either needs 2 or it needs 8. It only really needs 2 if it's really close to helium. What elements on your periodic table have the similar number of electrons to helium? Helium has 2. What elements have close to 2? How many does... What's a number real close to 2? 1. What element has 1? Hydrogen. So hydrogen usually emulates helium and tries to get to 2. What's another element number that's really close to 2? 3. What element has 3? Lithium. Lithium will also try to be like helium. It'll give away an electron. The rest of them, and a couple of exceptions we'll talk about later, try to get to 8, like the noble gases. What do I mean by that? Kirsten, find fluorine on your periodic table. How many does it have? How many more does it need to get to 8? So what it's probably going to do is it's flying through the universe. It's like, I've got 7 valence electrons. If only I could, hey, how you doing? And it makes a bond. And by making that bond, it's sharing electrons with the other element, and that bond will have 1 electron in it additional. It'll bond with other elements once. Nitrogen has, let's go to Aisha, find nitrogen on your periodic table. You count across, and how many does it have? You find nitrogen, you go 1, 2, 5. Do you need a periodic table? Oh. So I was just saying, how many valence electrons does it have? So you count across, go 1, 2, 3, 4, 5. Okay? So if it has 5, how many more does it need? How many more does it need to get to 8? 3. So it usually makes 3 bonds. Do you want to do it this way? Or that way? It depends on where you're from. How many does oxygen have? 6. How many bonds does it need to make? 2. Bromine has 7. How many bonds does it need to make? 1. You're trying to get them to 8. So they have a certain amount in their possession of their valence shell, and they're trying to get to 8. So chlorine has 7. Another chlorine has 7. They both need how many? They both have 7, so they both need 1. So they make one bond, and they share those electrons in common. That's the bond, the sharing of those electrons. And then afterwards you can go 1, 2, 3, 4, 5, 6, 7, 8, because they're being shared. 1, 2, 3, 4, 5, 6, 7, 8, because they're being shared. So after they bond together, they both have gotten to 8. That's your goal, is to get most of the elements to 8. Hydrogen is one of those cheaters. Hydrogen has 1. Hydrogen has 1. They share, they're at 2. What element has 2 valence electrons that hydrogen's emulating? Helium, yeah. There is a 7-step, not 7, idiot. There's a 5-step process that's in your notes. I don't use the 5-step process. If you find yourself struggling with how to do this, come to me and I can walk you through the 5-step process. We typically just kind of think it out. Hydrogen has 1 valence electron. Oxygen has 6. Oh, so, and there's another hydrogen, isn't there? Changed colors. How many does oxygen need if it has 6? It needs to make 2 bonds. How many does hydrogen need if it only has 1? Can't get to 7. So it can't do 8 electrons. But it can do 1 bond, which will get it to 2 electrons, just like helium. So you have to think 1 bonds, Russell, really? Whoa, that's a huge eraser. How could we put these pieces together? This is like Legos. How could we assemble this so that everything's got the right number of bonds? Who needs the most? Oxygen? So put that one in the middle. And then put the hydrogens on the outside. Draw the dots. 1, 2, 3, 4, 5, 6. Hey, I see that you put these together and those together, and that's by itself, and that's by itself. Why? Because I'm thinking ahead. I'm thinking, man, it's going to have to bond to both of these. I want to have plenty of space to make it happen. I want to be able to say, hey, these guys are going to share. These guys are going to share. Did I get everyone to the right amount now? Hydrogen's at 2, oxygen's at 8, hydrogen's at 2. And that's a pretty ugly drawing the way I've done it. So typically we would redraw that. The right way to draw it is to kind of go hydrogen, oxygen, kind of like that. So those electrons are trapped between the symbols for hydrogen and oxygen. All right, try the same thing with carbon. I'm going to pause while you guys practice. So we put carbon in the middle. It has 4 electrons. It's going to need to make 4 bonds. The oxygen's on each side because they need less. They're not as needy as the oxygen is. They don't need as much to get to 8. So the carbon shares twice with one oxygen, shares twice with the other oxygen. How many times has the carbon now shared? 4 times, which is what we said it was going to need to do. And the oxygen is sharing twice, and the other oxygen is sharing twice, which is what we said they were going to need to do. So we have carbon. Ooh, that's not a C. We have carbon. There we go. That's pretty ugly. But it is what it is. So the carbon is sharing with each oxygen twice. Is the carbon at 8 now? Yeah, you get to count 1, 2, 3, 4, 5, 6, 7, 8. Those are for both sides. And the last one here, the methane's pretty easy. Carbon has 4. Each hydrogen has 1. Sharing, 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 sharing. Does that drawing with the carbon and the 4 hydrogens look pretty balanced? Is it symmetrical? This and this are both gases, right? Methane, CH4 is this. What's it look like? Nothing. Because it's a gas and it's really what we call nonpolar. It's super balanced. It's not attracted to other things, so it stays as a gas. Carbon dioxide is also nonpolar, super balanced. Is water a gas at room temperature? No. It's not actually nonpolar. The way I've drawn it is a little deceptive. It's actually got a little bend to it, and that's these extra electrons. We're going to hit on that in a minute. All right. I'm going to pause. I want you guys to try to draw these two, GeBr4 and SF2. GeBr4 and SF2. So with the sulfur difluoride, you might notice that I put them at an angle, didn't I? I didn't put them directly across from each other. What? You don't have to. But typically when you have extra electrons like this on the atom in the middle, the atom in the middle has a very fancy name. It's called the central atom. I know, what a crazy name. When the central atom has extra electrons like this, we typically put the other ones at an angle. We do that because the actual three-dimensional model would be at an angle. When we build this model, we would pick one of the model pieces that has 4 holes. Those 4 holes aren't at 90-degree angles because this object, here we go, I'll actually do it in 2 ways. I have a couple of models here. This is at 90-degree angles, right? Agree? Yes, chugga 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 helps. If you make the chugga chugga noise, then the audience at home can see the thing I'm holding in my hand. That's not true. Don't look too hard. Yeah. So here I've got 2 models built, 4 directions, 4 directions. Which one has bigger angles? I'm going to merge them together. Which one has bigger angles? The yellow one or the blue one? Is it the blue one or the yellow one? I'm going to actually, if I can connect them. Haha. Line them up. Look at that, Abby. Which one's got a bigger angle? The blue one's angle, right, is bigger than 90. When you have 4, they don't go in a 90-degree angle. They go in what's called a tetrahedral shape. This is the tetrahedral shape. It's 4 pointing off in 4 separate directions. So one of the names we're going to learn in just a minute. Are there exceptions to these rules? There are 17 exceptions. We're going to learn 2. Okay? So the exceptions we're going to learn, and I'm just going to write them over here. We have hydrogen, beryllium, boron, most of them, and then we have phosphorus and sulfur. Oops. That looks like more exceptions than I just said. How many does hydrogen want? Good luck. How many does hydrogen want? It has 1 electron. How many does it? want to get to. Trying to get to 2. Beryllium is also a cheater. Beryllium only has 2 valence electrons. It's happy with 4. Boron has 3. It's happy with 6. Most of the periodic table is trying to get to 8, aren't they? And then we have phosphorus and sulfur. They're happy with 8, 10, or 12. What? So what you're going to do, Anna, is you're going to try to build the model for sulfur with 8. If you do it, then you're done. If you can't do it, then try to go for 10. If you can do it with 10, then you're done. If you can't, then try for 12. But 8's your starting point. So here's 2 of the exceptions right here. Boron with 3 fluorines. Boron has 3. Fluorine has 7. They share those 2. They share those 2. They share those 2. You might notice I put them in an angle. What shape did I just make with the 3 fluorines? Triangle. The name of that model, which we're going to look at in a second, is called triangle planar, as in a flat triangle. Wow. It's a crazy name. Flat triangle. Triangle planar. BeH2, beryllium to hydrogen to hydrogen. What shape does that look like it might be? Say again? That looks like a rectangle? Did you say rectangle? Okay. We have 3 things connected and they're straight. It's a line. Its name is linear, as models go, because it kind of looks like they make a straight line. What's the rectangle? I don't. If I outline the whole thing? I now understand the confusion. So what I was trying to ask was, you have these objects, fluorine, fluorine, and fluorine. They are kind of making a triangle. Like these are the vertexes of a triangle. You have these 3 objects. 1, 2, 3 objects. And they are in a line. Okay? I was confused, as it was mutual confusion. We agree on that? Okay. That's what happens when I try to go out of order. Here's a sulfur that won't follow the rules. It's actually one of my favorite gases. Sulfur has 6, sulfur has 6, sulfur has 6, and there's 6 fluorines. This is called sulfur hexafluoride. Sulfur hexafluoride's one of my favorite gases. So much so that I think we're going to pause for a second and watch a video about it. But I can't show you the video inside my video, so I'm just going to say Google cool videos on sulfur hexafluoride. So this molecule is so nonpolar, so balanced, if you will. Ah, my spelling's not very balanced. So nonpolar or balanced that even though it's really heavy, 6 times heavier than air, it's still a gas. Pretty rare gas, pretty weird gas. Pretty fun, though. Okay, so what we're going to shift into now is actually trying to talk about the 5 shapes. The 5 shapes, pretty simple if you actually see them and kind of think about them. The first one is linear. And in linear, guess what arrangement the 3 atoms make? A line. Very good. Does that look like a line? Not a rectangle. I'm throwing this across the room in anger. So when we draw that, there's 1 atom in the middle. There's 2 atoms on the outside. There we go. They are sharing these guys. Woo! Woo! Well, that's not quite sharing them all. Sharing them. Now, the key here is that you have two directions but zero extra electrons on the middle atom. Does the beryllium have extra dots or extra electrons on it? I hear you can see the no's, right? At home you can see everyone shaking their head no. Good. That's always helpful. So two directions, zero extra electrons. And that's really what I'm focusing on here is it's two directions, nothing extra on the beryllium. Hey, there's extras on the chlorine. It's on the outside. The shape is all determined by the inside. As you move them around, you have different angles. Held it close so that you get the sound effect at home. Water. Draw the Lewis dot structure for water. You have an oxygen with 6. You got a hydrogen with 1. A hydrogen with 1. They bond and share. Are there extra electrons on the oxygen? Meaning, most of the electrons, there's some of the electrons are in a bond, some of the electrons are in a bond. Ooh, these are not in a bond. These are not in the bond. So there's 2 that are in bonds and 2 that are not in bonds. There's extra pairs of electrons. Those extra pairs are going to bend the bonds. So when I push this pair onto here, these are too close now, aren't they? What's the angle there? What's the angle? There's a 90-degree angle. So what would happen is the electrons actually push these bonds away, and they start to shift and move around. They shift and move around until they get the maximum distance away. And so I have the gray ones are the bonds. The bonds and the tan ones are the non-bonded pair. We end up having an angle. And we call this shape bent. Why do you think it's probably called bent? Because the line, once the extra electrons are added, is then bent. Is that a pretty good name for it? It's a bent line versus a straight line. And you can really see it when you take the extras off that that's a bent line versus a straight line. All right. Our third shape. Put the boron in the middle. Put the 3 chlorines around it. What shape is this going to make, would you say? The chlorines make a... Still drawing crappy dots. There's it. Borons are making... the chlorines make a triangle, don't they? Do they have an extra pair of... Oh, there's like a bunch of things missing from this kit. Oh, no, there it is. Just kidding. 1, 2, 3. And then you put the extra pair, the atoms on. Triangle? Or flux capacitor? Hold it that way. You know what I mean by flux capacitor? Back to the Future. Good. So this is called triangle planar, or triangular planar, or trigonal planar. Why is it called planar? It's a triangle, and it's a flat plane, though, at the same time. Which brings us to our fourth shape, which is triangle pyramid. What do you think would happen if I tried to put an extra pair of electrons right here? What happens to these other bonds? Are they going to stay in those positions? This is electrons. They're negative. These bonds are negatives. What do negatives do to other negatives? Repel. And they do. They repel them into some angles. And they repel them into another triangle. Does that still look like a triangle? But is this triangle flat? No, it's called trigonal pyramid because it's got a slight pyramid shape to it. Not a full square pyramid, but it's got a triangle pyramid. So it's got the very fanciful name. Fanciful? It's not a word. It's really not. It's called trigonal pyramid. 3 that are kind of pushed down by that extra pair of electrons. And then our last shape, tetrahedral. Tetra means 4. Has anyone ever played the game Tetris? Yes, right? Tetris, each object has how many squares in it? The center one should be a C. You are correct. Better? In Tetris, each object has 4, whether it's the cube or the line or the S-shapey thing. They're all sets of 4 blocks. Tetra means 4. Hedra, though, similar to the word hydra, means 4, in this case, faces. So here I've built a tetrahedral here. It's 4 faces, 1 face on my hand right now, 2 face underneath, 3 face, 4 face. It means 4-faced object. Most people, though, just see that the bonds go in 4 directions, and that's what they remember, 4 directions for the bonds. Tetra means 4. That's the 5 shapes we're going to learn. There are 10 other shapes, but I think we'll put those off to AP Chemistry. Sound good? Take a look at your homework. Flip to Worksheet 1. There's a bunch of terms in Worksheet 1. And then on the back, what's on the back of Worksheet 1? Draw these shapes. You're going to try to draw these dot structures. You're going to try to draw how they're bonded together and take a guess at the name. Our lab is not by any means dangerous unless you have trouble controlling wooden sticks and things like that. You're going to build some models kind of like those that are hanging across the room. All right, and I'm done.